Alright, so this is going to be lecture 18. This is Coulomb friction in the pendulum. So hopefully we covered a numerical simulation on Monday the 17th, and this will be new material. Coulomb friction in the pendulum is a fairly short lecture. It's only 12 slides, so I think high confidence that we can get through this. So we've talked about vibration of linear systems in the past. We've talked about a mass spring damper system. We talked about just a mass and a spring. We talked about numerical simulation. We talked about overdamped, critically damped, and underdamped systems. And our focus was on underdamped systems. And we introduced the viscous damper as a means of dissipating energy in the system. And we noted that we don't always have that physical mechanism in the system. We don't always have a viscous damper in the system to dissipate the energy. Oftentimes what we have in the system is friction. So let's take a look at Coulomb friction and see what it will take to get our Coulomb friction into our equation of motion. So the force due to Coulomb friction, the magnitude of the force is proportional to the product of the normal force, vertical force, and coefficient of friction. Now, the magnitude of this force, it says it's proportional to the product of the vertical force and friction. That's the most that this friction force can generate. Okay, that's the maximum value that this friction force can generate. And normally, that's the amount of friction that is being generated. And we'll see that's a bit of a nuance that we'll see in a little while. Okay. The direction of this Coulomb damping, it always opposes the motion. Okay, it's always opposite the motion. So if the spring is moving to the right, the force is acting to the left. If the spring and mass are moving to the left, the force is acting to the right. So we're going to introduce this signum, this sine function, SGN. Okay, all that's going to do is look at the sine, SIGN, of the velocity. We'll see that in just a second. Goes always. We define our coordinates. So x, x dot, x double dot are all going to be acting to the right. Okay, all going to be positive to the right. That does not mean that that's always the direction that the mass is traveling. What that's doing is defining the positive sense for x, x dot, and x double dot. In this case, the positive sense for x, x dot, x double dot, all the derivatives are going to be to the right. Now we have to consider two cases. What happens when the velocity is negative, when x dot is less than 0? Not the position, but the velocity is less than 0. And what happens when the velocity is positive? So let's look at those two cases. So first case, the mass is going to be moving to the left. Okay? That means x dot is going to be negative. And the signum function, the sine function, SGN, is going to be negative 1. Okay? X dot is negative. This sine function is negative 1. All right? So far, so good. Now let's draw our free body diagram. And we'll draw these arrows with the appropriate directions. Okay? So the mass is moving to the left. Our spring force is going to be k times x directed to the left. So x is positive, kx is negative. So our spring force is drawn correctly as shown. What about our friction force, F sub c? Well, we said that the mass is moving to the left. The friction always opposes that velocity. So this arrow for the friction is going to be drawn to the right. Now, what's the magnitude, the maximum magnitude of this friction force? Well, it's going to be mu times the normal force, mu times mg. That's going to be the maximum friction force that can be developed and acts to the right. Okay? Now, let's write our equation of motion from our free body diagram. X double dot is positive to the right. There's a force that opposes that, k times x. So a minus kx would appear on the right side of this equation. What about this friction force, mu mg? That's acting in the same direction as x double dot. That arrow is acting in the same direction as x double dot. So it's going to be positive mu mg. Mx double dot minus kx minus mu mg. Now, what's this signum x thing? How come that got introduced there? Well, the way this is drawn is all correct. And we had a plus umg. What we want to do is include this signum function, this sine function. Okay? We started out with a plus, we changed this to a minus, and we introduced this signum function, which is a minus. So all we're doing is multiplying by -1 and -1 twice. Okay? So the bottom equation on the left-hand side is the same as the top equation on the left-hand side. What we're doing is multiplying by -1 times. Now let's consider the case where the mass is moving to the right. So x is positive to the right, the velocity is positive to the right in both those cases, but now the mass is moving, the velocity is to the right. Kx is still drawn correctly, so we talked about that in the first couple lectures. Now, our friction force is going to oppose the motion. The motion, the blue arrow, the motion is to the right. X dot is positive. The signum of that, the sine function of that, is +1. Derive our equation of motion from our free body diagram. Here's our free body diagram. All the arrows and the definitions of forces are written correctly. We've got the arrow for the spring pointing to the left with a positive kx. That's correct. Mx double dot is equal to minus kx to the left, and x double dot is positive to the right. So that's correct. And we have a minus mu mg. We're opposing the motion. The friction force, circled in green, opposes the velocity, the blue arrow on top. All right. Now, signum is +1. Okay, we can include this sine function, SPN of x dot on the bottom. Okay. All we're doing is multiplying by a +1 on the right side. Now, what do we have? If we look at these two bottom equations, because we've introduced this signum function, let me back up, because we introduced this sine function in here, which is nonlinear, because we introduced this nonlinear function, we're able to write the equation of motion for both these cases as the same equation. You see the bottom left is the same as the bottom right. By introducing this nonlinear term, we've got one nonlinear equation to describe both of these two cases. We don't have to simulate them separately. Okay. Two cases depend on the equation of motion. We introduce this sine function is used in a single nonlinear equation of motion. So here's our single nonlinear equation of motion. All we do is take everything that was on the right-hand side of the equation and move it over to the left-hand side. We see we have a function of acceleration, x double dot, a function of velocity, x dot, and a function of position, x. All right, so this sine function is nonlinear. Okay? One option we could have is we still can, solve this piecewise. So if we go back to these equations, what we can do is, let's say our initial conditions are such that our velocity starts off negative. We start off on the left-hand side. This top equation is our equation of motion for all times in which the velocity is negative. So if our initial conditions are negative, we can use this equation of motion. We can assume a form of our solution, substitute it in, find the conditions under which the assumed form is, the equation of motion is satisfied by the assumed form, and we can find a solution, and that will be valid anytime the velocity is negative. We would use that for all the beginning times when the velocity is negative until the velocity hits 0. After the velocity hits 0, it's going to go positive. Now we would solve this equation on the right-hand side. And this equation would be valid for all times in which the velocity is positive. And the velocity is positive, and so we would stop, go to 0, and then we would switch again. We would have to switch back and forth which equations are we going to use depending on whether the velocity is positive or the velocity is negative. Okay? That's what this slide means. We say we can solve it piecewise. We can solve this numerically. Okay? We can take time steps. We can evaluate. Is the velocity positive? Then use these equations. Is the velocity negative? Then use these other equations. There's going to be more than one equilibrium position. There's going to be a whole range of equilibrium positions. Okay? Because if there's a mass sliding back and forth attached to a spring, and it's sliding back and forth and there's friction, it can stop anywhere, any spot. I can set that system on the table, and it will stay put anytime the friction force exceeds the spring force. And we'll solve for what that is in just a second. We see that the decay, instead of an exponential decay, so we talked about viscous damping, and we found that we have that e to the minus zeta omega n t term, right? We have exponential decay when we have a viscous decay. That's different when we have this friction, energy loss through Coulomb friction. What we have is a linear decay. Decay is linear rather than exponential. When it comes to rest, whenever the spring force cannot overcome friction at an instant when the velocity is zero. Let's look a little more in depth. One thing, yes, note, it's not settled at x equals 0. So if you have viscous damping, eventually you have this exponential decay, and it continues to decay until it comes to that static equilibrium. Here, that's not the case. It's not going to settle at the static equilibrium. Matter of fact, there are going to be many static equilibria. Okay? It's going to be static whenever, it's going to come to rest whenever spring force cannot overcome the friction at some instant when the velocity is 0. Take a look at that. A little bit more depth. What is the period of this oscillation? Well, we remember back before we had damping. Okay, the period of an undamped system was 2 pi over omega n. When we had damped vibration, an underdamped system, we had t is equal to 2 pi over omega d. Now we have Coulomb friction, Coulomb damping. Now our period between oscillations is going to be 2 pi over omega n again. All right. What's the decrease in the amplitude? Well, let's see. The decrease in the amplitude is going to depend at, we've got our x naught here. We're going to lose this 4 mu n over k each full oscillation. Okay, so here's half an oscillation. You see we started at x naught. It's decaying linearly. So half a cycle down at the bottom, what the amplitude is, x naught, and then with the amplitude we're losing 2 mu n over k. After one complete cycle, how much are we losing? Well, we're losing twice that. X naught minus 4 mu n over k. Now we go 1.5 cycles. How much are we losing? Well, at this point, although it's not shown, it's going to be x naught minus 6 mu n over k, and so on. Now, so that's the way that it's going to decay. Now the question, here's the slope. Slope of that line. 2 mu n omega n over pi k. And we know how much it decays between this point and this point, and we know period between these points. So rise over run. The rise is going to be 4 mu n over k, and the distance is going to be 2 pi over omega n. You can do the algebra, you can find out the slope. Okay? The decrease in value between the peaks is going to be the rise at 4 mu n over k. The distance, the run, is going to be 2 pi over omega n. Rise over run, do the algebra, and you can get this slope. Now, when is it going to stop? When is it going to stop? Well, according to this, it stops right here. Okay, what's this mu static n over k thing? Take a look. All right. let's do an example. What is the coefficient of friction mu? All right, we're given the initial position is x naught is 1 meter. And we know that x at t equals capital T, 1 period, we've decreased to 0.9 meters. Okay, and the period is 1 second. So what is the coefficient of friction mu? Well, we have this decrease. We know we've decreased 0.1 meter, 100 millimeters in 1 second. Okay, that's how much we've decreased. So let's go back a slide. Okay, we've decreased by, our decrease. We've decreased by 100 millimeters. And we know this is 1 second. Here's our slope. So let's see if we can find the answer. Ooh, a little bit handwritten. We know our period. We know our natural frequency. Natural frequency is K over M. And here's how much we've lost per cycle. Okay? In our case, we know the amount that we've lost in one complete cycle is 4 mu mg over K. So in our case, we know 4 mu mg over K is 100 millimeters. 4 mu g over, what's this? K over m, that's omega n squared. Right? Is equal to 0.1 meters. What's omega n squared? We can get that from the period. We know the period is 1 second. So we know that our omega n squared is going to be this 2 pi radians per second, whole thing squared. Okay? So we know 4 mu g over omega n squared is 1/10 of a meter. We can rearrange this term and solve for mu. So mu is going to be 0.1. Here's our 0.1. Divide by 4g, so multiply by omega n squared, 2 pi radians per second squared. And we get damping of about 0.1. You should try to solve this on your own. Walk through this problem on your own. See if you can solve for mu, the coefficient of friction. Now, how do you make the system stop? So we'll go through this MATLAB code in here. Okay? I'll just give this to you. This is how we're going to check and see if the system is going to stop moving. Okay? We're going to look and see if the absolute value of the velocity is less than some very small tolerance. Now, when you're doing these numerical simulations, odds of you predicting at these discrete steps of getting the velocity exactly equal to 0 is extremely small. So what you have to do is not find when the velocity comes to 0, but when the velocity, the absolute value of the velocity, the speed, is extremely small. Some very small tolerances. Let's call that tolerance tau. And let's set it to 0.0001. Okay? For now. Let's use that tolerance. Okay? If the velocity is lower than this tolerance, and then what's this? What's this saying? Okay? What's mu times m times g? Well, that's the friction force, the maximum amount of friction force. And what's k times x? That's the spring force. What this is saying is, if the velocity is very, very, very small, approximately equal to 0, very close to 0, as close to 0 as we can get using numerical simulation, and the friction force is greater than the spring force, then we're going to stop moving. When it stops moving, equilibrium, right? X dots are 0. That's what equilibrium is all about. So x dot 1 is 0 and x dot 2 is 0. All right. When does the system stop moving? Back up. The system is going to stop moving whenever the friction force is greater than that spring force and the velocity. All right, couple quick points. Summary of nonlinear vibrations. We have some additional phenomena with linear case. We have multiple equilibrium positions. So that mass, when it's sliding back and forth, can stop and stay anywhere. And the velocity is zero, and that friction force is greater than the spring force at that moment when it's stopping. Instabilities are possible with positive coefficients. We haven't looked at that yet. Form of the response is dependent on the initial condition. Closed form solution, usually not available, but we can simulate it numerically. A linear model has tremendous advantages. I'm just reading these now. Linear combination of inputs yields linear combination of outputs. We're going to explore some of these in more depth later on. The big takeaways from this are understanding the linear decay of these Coulomb, and get my mouse to work. And no, those. Thank you.